Hi everyone, thank you for virtually attending this talk. This is a joint work with Badih, Ghazi, Ravi, Kumar, and Rasmus. Pagh. In this work, we consider the setting of distributed data analytics where there are end users and there is the analyzer. Each user I receive an input xi, and based on this input and his or her private randomness, the user produces a message yi. These messages are sent to the analyzer, who then use them to compute an estimate of some function f on the input xi to xn. Throughout this talk, we will focus on the case of binary summation. This is the task where each xi is just either 0 or 1, and our goal is just to compute the estimate of the sum of x1 to xn. This is a very basic task that is used as a building block for many more advanced algorithms. Now, we would like to compute this sum privately. And the notion of privacy we'll be using is the differential privacy notion by De Walk and others. Intuitively speaking, differential privacy says that if we change an input to a single user, then the distribution of the output shouldn't change too much. Specifically, there are two parameters in differential privacy, epsilon and delta. We say that an algorithm is epsilon delta differentially private, or epsilon delta dp for short, if the following condition holds. When we look at any two neighboring datasets, which means that these two datasets differ on a single user's input, and if we look at any set of possible outcome S, then the probability that the algorithm output any outcome in S on the first dataset is at most e to the epsilon times the probability that the algorithm output any outcome in S in the second dataset plus delta. For those of you who haven't seen the notion of differential privacy before, epsilon here should be thought of as a small constant, such as 0.1 or 1, whereas delta should be thought of as very, very small, for example, 1 over n to the 10 or 1 over 2 to the n to the 0.1. As many of you might have already noticed, we haven't been very formal about what we consider to be an algorithm. Indeed, a different scope of the algorithm will give rise to different notion of differential privacy. On the one end of the spectrum, we can consider the entire process as a single algorithm. In this case, we only want the output of the analyzer, which is the estimate itself, to be differentially private. This is indeed the model that was originally considered in the work of De Walk et al. And this is now sometimes referred to as the central model or the curator model. This model is really great in terms of error. Already in the original work of De Walk et al., they gave an algorithm called the Laplace mechanism that can achieve an error of 1 over epsilon for the task of binary summation. So when epsilon is constant, this error is also constant. And in fact, this algorithm has delta equal to 0. It's common in literature to write epsilon 0 dp as just epsilon dp, and we will do the same in this talk. While the central model is great in terms of error, it requires a pretty strong trust assumption. For example, the analyzer can even see users' raw input, which might be undesirable in some applications. This leads researchers to try to come up with a model that requires weaker trust assumption. Arguably, the most popular of which is the so-called local model. In the local model, we think of each user's randomizer as the algorithm. Hence, we are requiring the messages sent by the user to be differentially private. So this is really great in terms of trust assumption because everything that is sent by the user is differentially private. Unfortunately, it's known that we have to incur a large error in the local model. Specifically for the task of binary summation, it's known that the error has to grow with square root n, and this can be achieved by the simple randomized response algorithm. Given the large error incurred in the local model and the strong trust assumption required in the central model, there are also other models that are proposed in an attempt to keep an error pretty low, similar to the central model, while not requiring quite as strong trust assumption. We'll be working in one such model called the shuffle model. The overall setting is pretty similar to before, except that instead of the messages yi's being sent to the analyzer directly, there is a shuffler in between that randomly permutes the messages before sending them to the analyzer. The requirement here is that the shuffled messages have to be differentially private, or equivalently, that the multi-set of the messages have to be differentially private. In this case, the users don't have to trust the analyzer. Rather, they only have to trust that the shuffling actually occurs. Now, there are multiple ways to implement secure shuffling, and this is beyond the scope of this work. So we will always think about the shuffler in the middle as a black box for the purpose of this talk. This model has been referred to using different names, including the anonymous model. So this is mostly used in the field of cryptography. In the differential privacy literature, it's either referred to as the encode shuffle analyze architecture or the shuffle model. A fundamental result in the shuffle model that helps contribute to its popularity is the so-called amplification by shuffling theorem, which was proved by Erklingson et al. And later improved by Badih et al. The theorem states the following: if we take any epsilon local dp, but run it in the shuffle model instead, then it's actually epsilon delta dp in the shuffle model, but with a much smaller epsilon than before. And this holds for reasonable value of delta. In other words, we get a saving in terms of privacy, specifically in terms of epsilon, almost for free if we just look at the algorithm in the shuffle model instead of in the local model. In other words, for a similar level of privacy, the shuffle model almost always automatically incurs smaller loss than the local model. Alright, let's now go back to discuss about the binary summation problem, what was known, and what we proved in this paper. In addition to the error, we will also be concerned about the communication complexity, which is measured by the number of bits sent per user. So in the central model, recall again that the Laplace mechanism can solve this problem with error 1 over epsilon, and the number of bits sent per user is just 1, so each user just sends his or her own input. In the local model, again, the error grows with square root n, and there's an algorithm that can match this bound, which is the randomized response. And in the randomized response, each user also sends just a single bit. Now we move on to the shuffle model. If we use the amplification by shuffling result from the previous slide and just run the same algorithm as in the local model, which in this case is the randomized response algorithm, then we immediately get an improvement in terms of privacy. Equivalently, this means that if we want a similar level of privacy, we get an improvement in terms of error. Specifically, if we want an epsilon delta dp in the shuffle model, randomized response only incur an error of square root of log 1 over delta over epsilon. And notice that this can be much smaller than square root n error incurred in the local model when delta is not too small. However, the error that we get here still doesn't match with the error that we get in the central dp. There is no dependency on 1 over delta at all, whereas here we are paying square root of log 1 over delta. So question here is whether we can get rid of this square root of log 1 over delta. And this brings us to the first result of this paper. So we show that we have to incur this square root of log 1 over delta in terms of the error if each user can only send a single message. Now this means that if we want an error that depends purely on 1 over epsilon, similar to in the central model, we have to allow each user to send multiple messages. Pictorially, now the algorithms will look something like this, where each user I can send up to di messages, and all the messages together are shuffled before they are revealed to the analyzer. It turns out that once we look at this multi-message setting, it is indeed possible to achieve error similar to central DP. In particular, a line of work by Xu et al., Ballet et al., and then Ghazi et al. Eventually achieved an algorithm with error order of 1 over epsilon, whereas the communication complexity per user is roughly log n over delta bits. This is still pretty large considering that before each user was sending only just 1 bit. This brings us to the second and the main result of this paper. We give an algorithm that achieves an error similar to central DP, whereas each user is sending only slightly over 1 bit in expectation. In particular, the expected number of bits sent by each user is 1 plus order of log square of 1 over delta over n. And this second term will be little of 1 when delta is not too small. In other words, we achieve nearly the same error as in the central model, while also incurring almost no communication overhead at all. Before we move on, we would like to note that all the algorithms that we discussed so far in the shuffle model, including the ones in this paper, only work in the case where delta is greater than 0. In another recent work, we in fact give an algorithm for binary summation that work even when delta is equal to 0. However, the error is still pretty large. It's not the same order as in the central model, and in fact, this big O has a pretty large constant here. And also the number of bits sent per user is log n, which is also pretty large. We will not discuss this other work further here. In the remainder of this talk, we will outline the key ideas that underlie our main algorithm. To understand our algorithm, we have to first recall the algorithms in the central model. In a central setting, typical algorithms work as follows. First, each user can just send his or her own input directly to the analyzer because we are in the central model. The analyzer then computes the true sum and then add to it some noise, and this noise will be drawn from some distribution D. For the purpose of this talk, sometimes we will write the D itself instead of the noise in the sum for brevity. Different noise distributions will lead to different privacy and error guarantees for the algorithm. For us, the only noise we have to care about is the discrete Laplace noise. This is a distribution over all integers where the probability mass at I is proportional to e to the minus epsilon times the absolute value of I. It's not very hard to see that this algorithm is epsilon dp in the central model and that the error is of the order of 1 over epsilon. More importantly, is in fact known that this algorithm with a slight modification is optimal among all the epsilon dp algorithms in the central model. In other words, this discrete Laplace mechanism is the gold standard that we would like to match in the shuffle model. One key idea that will be needed in coming up with an algorithm in the shuffle model is to dividing the noise among the users. And to do so, we use a concept from mathematics called infinite divisibility. Specifically for distribution D, we say that it is infinitely divisible if for every positive integer n, we can find another distribution which we denote by D subscript divided by n, such that if we take n independent identically distributed sample from D over n and take their sum, then this sum is distributed the same as D. In other words, this original distribution D can be divided into n identical parts. There are already quite a few natural distributions that are infinitely divisible. For example, you might have seen before an identity that the Poisson distribution is infinitely divisible. Another family is the negative binomial distribution, which can be viewed as a generalization of the Poisson distribution. And most importantly, the discrete Laplace distribution themselves are infinitely divisible just because they can be written as a difference between two negative binomials. It's not too important in this talk what exactly these distributions are, but one thing I would like to note here is that the Poisson and negative binomial distribution are distribution over non-negative integers. On the other hand, the discrete Laplace distributions are over all integers. meaning that they can also take negative values. It will be clear in the next slide why this distinction is important. Now that we have infinite divisibility concept in mind, let's try to use it to come up with an algorithm in the shuffle model. So let's say our algorithm has two parameters, an infinitely divisible distribution D, which is also the noise distribution we want to eventually add, and the number of users N. Our algorithm will be very simple. It will take in the X, the input either 0 or 1, and the messages that it sends will all be the same, which I denote by 1 in this case. But the number of messages sent will be a random variable, which is generated as follows. So first we sample a random variable C based on the distribution D divided by N. And then the number of messages that we send is C plus X. The analyzer here is also very simple. Just return the sum of all the messages, which is of course also equal to the number of messages. Now let us do the privacy and utility analysis of this algorithm. To do so, observe that all the analyzer sees is just a bunch of ones. So the only thing that it learns is just the number of these ones. And the number of these ones is exactly equal to the sum of xi plus the noise term z. And there are n independent copies of this noise, where each of them is sampled from d divided by n. So by the infinite divisibility of d, this sum of noise has distribution exactly the same as d. So from the analyzer viewpoint, the number of ones is exactly equals to the sum of xi plus a noise drawn from d. In other words, in terms of privacy and utility, this algorithm has exactly the same privacy and utility as the additive noise mechanism that adds noise from distribution d in the central model. Now recall from the previous slide that the discrete Laplace distribution itself is also infinitely divisible. So can we just plug d equals to discrete Laplace here and be done? Well, not really. The problem here is that our algorithm is in fact not well defined if the z can be negative, because we cannot send, let's say, -1 or -2 messages. And indeed, this algorithm is only well defined when the distribution d is over non-negative integers. Now, the fact that d has to be non-negative alone doesn't mean that this algorithm cannot work for us. As we saw before in the previous slide, there are a bunch of non-negative distributions that are infinitely divisible, such as Poisson and negative binomial. Unfortunately, here we can show that if we just use this algorithm over non-negative distribution d, then we will still have to incur an error that grows with square root of log 1 over delta. So we do need a different algorithm. Alright, let's try to modify our algorithm a little bit. Since we want to handle also negative noise, it's pretty natural to send messages that are both +1 and also -1. The algorithm is very similar to before. In the first step, we sample z, but now we also sample z minus from the same distribution. The number of +1 we are sending is the same as before, is z plus the input x, but we are also sending the minus, and the number of -1 that we are sending is z minus. The analyzer is exactly the same as before, just to return the sum of all the messages. Now let us analyze this algorithm. To do so, once again, we think of what the analyzer sees. Now the analyzer sees a bunch of +1 and a bunch of -1. So what the analyzer actually sees is the number of +1 and the number of -1. And once again, the number of +1 is the same as the previous case, which is just the sum of xi plus a noise drawn from distribution d. But now we also have the number of -1, which is just the sum of the z minus. And indeed, this sum has the same distribution as d. Now in terms of utility, since the analyzer estimate is just the sum of all the messages, this is equals to the number of +1 that the analyzer sees minus the number of -1, which is just equals to the sum of xi plus a noise drawn from distribution d minus an independent noise drawn also from distribution d. Now if we set d to be a negative binomial distribution with appropriate parameters, then the difference of two independent samples drawn from d will have exactly the same distribution as the discrete Laplace distribution. What this means is that this algorithm will incur exactly the same error as the discrete Laplace mechanism in the central model, which is really great. Okay, so we are good on the utility front. How about on the privacy front? Unfortunately, we are not so lucky there. We won't have time to go into too much detail why this algorithm is not as private as we would have hoped for. However, the intuition here is that the analyzer can still see the number of ones, and the number of ones here is the true sum of xi plus a noise. But this noise is drawn from the negative binomial distribution, which it turns out that this is not as private as if the noise were drawn from the discrete Laplace distribution. In other words, we somehow want to add some more noise to the number of ones to make our algorithm more private. However, we want to do so in such a way that it doesn't affect the accuracy of the algorithm. So with this in mind, let us move on and revise the algorithm one more time to get the final version of a working algorithm. So here is the final version of our algorithm. It's extremely similar to the algorithm from the previous slide with only one modification. We are also sending y additional plus 1 messages and y additional minus 1 messages, where this y is a random variable that is drawn from a distribution d prime divided by n, where d prime is some other infinitely divisible distribution. The analyzer here is exactly the same as before, just return the sum of all the messages. In terms of parameter selection, similar to before, we select the noise d to be the negative binomial distribution in such a way that the difference of two copies of the noise is distributed as the discrete Laplace distribution. However, this time we set the parameter a little bit more aggressively so that the discrete Laplace here is a discrete Laplace with 0.99 epsilon differential privacy guarantee instead of epsilon differential privacy guarantee as before. It's not too important here, and it's mostly a technical point, so you don't have to worry about the 0.99 here too much. What is more important though is that we are setting d prime to also be a negative binomial, but with a much larger magnitude. In particular, the mean of d prime will be something like log square of 1 over delta, whereas the mean of d is only of the order of 1 over epsilon only. So although this noise d prime is quite large, it doesn't affect the accuracy at all because we are sending y plus ones, but we are also sending y minus ones as well. So when the analyzer sum up all the messages, these plus 1 and minus 1 additional messages will all cancel out, and we end up with the same accuracy as the discrete Laplace mechanism, that is 0.99 epsilon differentially private in the central model. In terms of privacy, however, this noise d prime is actually very useful because the noise d prime helps hide any useful information in the number of plus ones, and this helps us overcome the problem that we had with our previous algorithm. We don't have time to see the full proof today, but it's indeed possible to show that this algorithm is epsilon delta differentially private in the shuffle model. One thing that we have neglected so far in our analysis is the communication complexity. So let's briefly argue about our algorithm's communication complexity. First of all, each message that we are sending is either plus 1 or minus 1, so we can represent them using a single bit. Hence, we only need to compute the expected number of messages sent per user. So this number is exactly equals to the expectation of x plus z plus c minus plus 2 times y. Now, x is either 0 or 1, so the first term is at most 1. The expectation of both z and c minus is equal to the expectation of d divided by n, whereas the expectation of y is equal to the expectation of d prime divided by n. Now we can simplify this further because the expectation of d divided by n is just equal to the expectation of d before the division and then divided by n. And the same goes with d prime, so we get this simplified term here. Finally, note that expectation of d is of order of only 1 over epsilon, whereas expectation of d prime is of order of log square of 1 over delta. So the whole expected number of messages sent is just 1 plus the order of log square 1 over delta divided by n. When delta is not too small, specifically delta is at least 1 over 2 to the little o of square root n, this second term is little o of 1. So virtually there's almost no communication overhead at all per user in expectation. And that concludes the analysis of our algorithm. Just to recap, in this paper we give an epsilon delta DP protocol in the shuffle model for binary summation that achieve an error almost the same as the epsilon DP protocol in the central model. Furthermore, the expected communication per user is only 1 plus little or 1 bits for a reasonable but not too small value of delta. Finally, we don't have time to look into it today, but our protocol can also be used to solve the histogram problem, and it gives a similar guarantee for the case where the number of buckets B is much smaller than n. Let us end on two open questions. First, even though our protocol has expected communication just 1 plus little or 1 bits, it's still open whether we can get this expectation down to just at most 1 bit. So that would mean basically that there is no communication overhead at all. Second, our histogram protocol has small communication complexity only in the case where the number of buckets B is much smaller than n. The communication blows up significantly when B is larger than n. So the question here is whether we can give a communication efficient protocol for the case of B much larger than n in the shuffle model for the histogram problem. And with that, thank you very much for your attention.